All right, Mr. Claxton's algebra. Whoop, you're not algebra. You would be digital electronics students. Sorry about that. Just got done churning out some algebra videos there. Looking at this presentation, what do you need to know? What is very important for you to know? You need to be able to define clearly analog and digital signals and compare and contrast analog and digital signals. So thinking about analog and digital signals, analog, we are thinking a clock, like an analog clock that has arms that smoothly go around in a circle. And then we have digital signals. Think of a digital clock. Digital clock will tell you that it is 6:45 a.m. It does not give you the number of seconds. It can, but it does not give you that very exact and continuous like an analog clock would. An analog clock, you could tell exactly how far you were through that 6:45 a.m. You would know 6:45 and 55 seconds, 56 seconds, all the way up to 6:46 a.m. They go with thermostats too. If you've ever looked at a digital thermostat before, maybe I can get a picture of one here for you. A digital thermostat will just print it's 71 degrees. You'll see it. But if you look at an analog or another type of thermostat, maybe you've seen the round ones before in an older house, it has mercury in it, and that mercury will go up to a certain point. So you might see like 72 and then almost halfway through, like 72.482 degrees. So that is one very specific example. I do want you to come up with other examples. I would like you to also share them with your peers. We will have a discussion board to do that later. So this is a very important slide for differentiating between analog and digital signals. You do not have to write down everything, but it might be nice to have, if you want to write down just these key points right here. And this is what differentiates analog from digital. It gives you some examples here. I want to note, just make a note, this is a square wave. It's not a digital signal because it goes below, and most of you know this already. I integrated this question into your most recent assessment, but this goes below what we call the zero line here. So because it goes into the negative, this is an analog signal. It's just known as a square wave. So you see 0 volts right there. If it goes below 0, it is going to be an analog signal. Digital signals stay above 0 volts. Parts of an analog signal, you see, students of pre-calc, which probably aren't very many of you that are in pre-calc, but you see the amplitude of the wave. Now there's peak to peak amplitude and just peak. So make sure that you differentiate between that in your examples. That would be my daughter calling my dog Benji right now. So you might hear my daughter calling Benji. All right, excuse me there. I had to ask my daughter and son to keep it down here. So we look at the period, which is just the length of the wave, start to finish. So start, if I can make a point right there, to finish, make a point right here. I like to, when I'm teaching in class, I like to go ahead and highlight just, this is just the length of the wave, and we have our wave here, and then the length is the period, just start to finish, start to finish. We call that T. So when we take 1 and divide it by the length of that wave, it will give us the frequency in hertz. So that will give us the frequency in hertz whenever we take 1 and divide it by the period. Looking at these logic levels, this is an important slide. I am going to print this off for you for the rest of the year. We will we will use this. You already should have been exposed to this information, but we will define 2 volts to 5 volts as a logic high and 0 volts to 8/10 of a volt as a logic low, and it will be invalid. Anything in between will be invalid. So the only thing right here that you would need to copy down would be this if you were taking notes. We see examples of digital signals. Just notice how none of these go below 0 volts. None of them go below 0 volts. And again, you can read the information there. We look at time high, so I would like to go ahead and show you here about time high and time low. So I can go ahead, let me go ahead and access the pointer options here. All right, sorry about that. So we see that time high is just this length right here. That's called time high. And that's T sub H is what you're seeing up here. Time low would be, it's either high or it's low. So time low would be this, when is it at 0 volts? So we can see that the time low there is quite a bit longer than the time high. Now our period is still the start to finish. So start to finish would be from the start of the wave to the end of the wave. So we look here, the time, the amount of time that this is high is called the duty cycle, the percentage. And I think that's in the next slide there that we show you that all the features of a digital signal. So this is what you're going to refer back to when you're doing those problems on the activity. You're going to have this in front of you, maybe for the first one, and then, don't look at it for the second example. You will need to remember this information, and there will be a Quizlet coming with, this information so you can study this. But for the time being, use your resources, use what's here in front of you to study the frequency and duty cycle and the parts of the digital signal, as well as, go back and review the parts of the analog signal as well. And a lot of this is intuitive. We see time high and time low, which I just explained. We see an amplitude from 0 volts to whatever the top is. And then we see a falling edge. As you can hear my son yelling in the background. So what do we have as far as duty cycle? Duty cycle is the percentage of time that the signal is working. So the percentage of time that is high. So if you look up here, what percentage of the time does that signal have a high signal? And it's over 50% here. So it's going to be over 50% for this one. So just to kind of estimate what the duty cycle is. Now you're going to take the time high, whatever the time high is, however long that it's high, however many nanoseconds or microseconds or milliseconds that the signal is high, and you're going to divide it by the period, which is the length of the signal. So we see the length of the signal there. The length of the signal is start to finish. So we're going to take this value up here and divide it by that period. Then we multiply it by 100 to convert it to a percentage. So we know that this one's going to be over 50%. I could look at the scale down here to get a better estimate of what that is, but I know it's going to be over 50%. The oscilloscope, well, you know what, I'm just going to save the O-scope for a later. Mr. Pry does have one that I can go get and that I show you. I show you what an O-scope is. We use a virtual version of the O-scope. So when you see the virtual version, it's going to look like this. The dial, the virtual dial, is down here. You would click on that to get the different signals. So that's what you have to click on when we're on Multisim, and I can show you that. It looks like this when we're in Multisim, and then you double click on this icon right here once you put it on your worksheet to get this view right here. So All right, so if you are looking at an oscope, what do you need to know right now? Well, you need to know what the time base is, what the scale is. The scale is 1 millisecond per division. So what that means is per division, I'll show you what that means. Go ahead and grab the red pen here. So 1 millisecond per division would be 1 millisecond for each one of these right here. You see the grayed out dashed lines? So that's 1 millisecond. So if we look here, if this is the start, which it looks like it is, that would be 1 millisecond, 2 millisecond, 3 millisecond, 4 millisecond, 5 millisecond, 6 milliseconds long. So our period length would be 6 milliseconds. Now there are ways to measure that I will show you in Multisim, and that's what they're showing you right here. Do not be confused by those. We will do that in Multisim when I get back. Looking here, what is the scale for basically the voltage, right? So the voltage is up and down. That is your y-axis. So 5 volts per division would mean that this would be 5 volts and then this would be 5 volts. So this would be a 10 volt power supply. So 5, 10 volt power supply there. And again, we'd have a 6 millisecond period. We could also estimate time high and time low. Time high would be, well, I've got 1 millisecond, so not quite 2. And if you go down here, you see 1, 2, 3, 4. So there's 5 different intervals in there. So each one of these is 0.2. So 1.2, 1.4, 1.6, 1.8. So this would be 1.8 milliseconds. That is an M there, right? And if I know it's 6 milliseconds long, then I can take 6 minus 1.8 to get 4.2 for the time low. So you can use some math here. Just make sure that you use the correct units. And that really should help you out with the activity. You should be able to stop now and do the activity and make the calculations based on what you know. I don't want to take up all your time, but I did want to give you an idea of what you needed to know. What do you really need to know that's part of this analog versus digital signals?